Right. Okay, guys, let's get started. So I think we are on week 9. This is week 9. Keep in mind the next exam is going to be week 12, and that week we have two exams, right? The written exam on Tuesday and then a practical exam, which is a fun event, really. That I usually call the scavenger hunt, so think of it that way. And so as I've said, I'll be hiding a message, right? And you have to break several encryptions. And I create like a theme, like there's three banks, and you break into three banks, steal the keys, and then once you have all three keys, you can actually open the message, right? But the key is every bank is a different technique. Like one thing will be RSA, one thing will be, you know, AES or DES or something like that. Make sense? So it's everything we've covered so far this semester. I still need to give you certain things for it. So the lab this Thursday is going to introduce PyCryptoDome. So that's a library in Python that's very powerful. So instead of writing the code from scratch, you can just, use some commands. So that's going to be the lab. That's going to come with an assignment that you have to demo. So you will have, and like I'll sit with you guys on a Thursday and you need to show me what you did, right? Because I need to understand, make sure that you understand actually how to do all the encryption steps. Okay, so we'll talk about that on Thursday, but that's also going to be part of the scavenger hunt, as we will be using a lot of those scripts to do the encryptions and decryptions. Got it? Today should be an interesting topic. I'll continue the discussion with RSA, but we're going to focus a lot on breaking RSA. So I'll give you today the two tools that we can use for breaking RSA, which are um, something called FactorDB, which is just a website, and then we're going to use a library from Python that simulates a quantum computer. So the idea would be that we're going to use the factorization algorithm, right, to break RSA. Okay. So I'll review today the algorithm again, RSA, how it works. We'll do a couple of problems. And then after that, we'll start trying to figure out how to break RSA. And then there might be like a short little quiz at the end where you guys have to try. And it'll give you, if anything, good practice on what's coming up for the scavenger hunt. So you have to understand you have a cipher, right? And the goal is to get what? The message or something like that. And the message, when you're using RSA, is what? A key. Got it? So that's essentially the plan for today. And then, as I said, on Thursday, we're going to look at PyCryptoDome. So we just have to make sure that we can install that library, which we should be able to now that you guys have Anaconda on your environment. All right. Yeah, so that's the plan for the next this week. Next week, just finish up our RSA, finish up breaking RSA, and then PyCryptoDome before we move on to other topics like Diffie-Hellman. So that's going to be the next topic, elliptic curves and things like that. Right. So if you remember, we're in the second third of the semester, and the focus this semester is asymmetric encryption, which is usually for key exchange. So the algorithms here are Diffie-Hellman, elliptic curves, and RSA, which are essentially for that key establishment. All right. So yeah. So I'll switch over to the whiteboard, and we're just going to practice some of these things, and then we'll probably fire up the VM. Okay, for breaking RSA, usually the script that you're going to use is the one that we used Thursday, right? So the that RSA encryption algorithm is the one that will allow you, right, to somehow break RSA. So let's okay. Here it is, option. Okay, so we're going to switch to the whiteboard. Yep. And like I said, there will be a little quiz at the end. All right, so remember, we're just covering RSA. I'm not really giving a new algorithm today. It's essentially just doing two more problems. But as you know, I'm filling in some of the things, right? So some of the assumptions, et cetera, some of the steps, I'm going to provide a little bit more context now that you understand how RSA works, so that we can, get more of how what the details are. So, I'll just kind of review. So the RSA algorithm for public key cryptography, as you know, it involves a public and a private key. So the steps to the process are that we need to select two prime numbers, P and Q, right? And you saw this on that script that we went over on Thursday. You saw that those are actually really large numbers, right? So they were massive. Obviously, for our problems that we're going to do by hand, we have to use smaller numbers. So we select two distinctive prime numbers, P and Q, and then we compute N. So it's going to be P times Q. So the central point of breaking RSA is obtaining N and reversing from N to P and Q and obtaining those two prime numbers. Okay? So that's essentially the idea. So let's imagine an example here. Okay, so we're going to have an example. We're going to pick another two prime numbers. In this case, P is going to be 17 and Q is going to be 43. Right, so small numbers. So now the next step is to compute N. So that's going to be P times Q, which is going to be 17 times 43, which is 731. Okay? As you know, one key assumption here is that N is going to be made public, and that's how you can obtain N. It's in the public key. So in the public key, you're going to have E comma N. So your goal is to be able to break N, factorize it to obtain P and Q. We also have this other value phi, which once you've broken N to obtain P and Q, you can calculate phi because we know that it's all it is P minus 1 times Q minus 1. All right, so in our example that we're doing here, it's going to be 16 times 42, which is equal to 672. Okay. Then, of course, once we have all this information, we can calculate D and E. Well, E is actually available, so you just need to calculate D. And you can use that algorithm that I provided. So the key thing is you just need to figure out P and Q, and you can use the code to solve the rest. So some of the rules. So D is smaller than N. So these are some of the rules for D, some additional information. Some rules for D. D is smaller than N. Okay. And D and phi have no common factors other than 1. Factors other than 1. Okay. So in this case, remember that we have to meet these conditions, but we can't just solve this analytically. We have to use algorithms, as we saw in the code, to be able to find these values. So in this case, for this scenario, D can be equal to 205, for instance, which in this case, if we go back, 205 is less than N, which is 731. So 731. So it meets that condition. And then we can look at phi. So the other condition, D and phi have no common factors. So we can kind of look at this like this. So we have D 205 and we have phi 672. So if we kind of factorize this a little bit, we have 5 and 41. And then over here we have 672 will be 2 times 2. Let's just do dot, dot, dot times 2. There's several 2's in there. Times 3. Times 3 times 7. So this starts to get at the heart of factorization, right? So we have to meet these conditions so it's hard to break. Do you guys see that? Otherwise, cryptanalytics would allow you to break it, essentially. So that's what the conditions are for. And that's why we have to use the specific approach. So no common factors. All right. So this is sort of the idea. And of course, E is another value that we have available, which in this case is 613. Right, which is another, we know how to get that as well. Right. Yeah, so we have, oh, sorry, E is 617 actually for this example. Okay. And then you guys know that we use these values to encrypt and decrypt. So this is just sort of a review. Okay. Now let's start going deeper into the process. Okay, we're gonna do here it is. All right. So now we're gonna let's do another example. And this time, let's focus on the E part and how that works. Okay, and the algorithm. So let's consider another example. Let's call it example 2. Okay. Again, let's select 2 prime numbers. So select 2 prime numbers, P equal 11 and Q equal 13. Okay, same thing. We calculate N. That's going to be P times Q, which is 11 times 13. And that's going to be 143. Okay, then we have phi. And that's going to be P minus 1 times Q minus 1. So this is going to be 10 times 12, which is 120. All right. So now, how do we get E? So if you remember, I just said something like E is less than phi, but also it meets some additional constraints. The constraint that it needs to meet is something called the GCD, which was in the code, the GCD. All right. So we're gonna just do an example here just to see how that works. Although remember, you wouldn't manually do this. This is done by the algorithm, but this is just so you get a sense of how this works. So we need to find, essentially it's a search, right? So we need to find an E that meets this condition of being less than 120, which is phi, but also that let's see if I can write this down here. We need to find an E that has a GCD of 1 with phi. That's the definition. Okay? So we need to find, so now this is the additional step. We need an E that meets this condition, and also we need E to have a GCD of 1 with phi. So what is GCD? Do you guys remember what GCD is? You learned this in like third grade, right? Yeah, exactly, right? So the GCD is the greatest common divisor, something that you did already, pure arithmetic, right? So let's define it here somewhere. So let's do GCD. And so it's an exhaustive search, right? So you have an E, you try it. Does it meet this condition? Is it less than phi? No. Okay, try another one. And you keep doing that. And as we will see, as it turns out, sometimes 65,000, whatever that number was, works all the time. And so that is commonly used. But let's define GCD here. So it's the greatest common divisor. Common divisor. So this, as someone said, is the largest positive integer. Is the largest positive integer that divides each of two integers. Each of two integers. Okay? So that's just something you've already seen before, but that's actually one of the conditions that E needs to meet for it to work, essentially. Okay, guys? So GCD. So as I said, this is going to be a search. So you got your P and Q, you calculated your N and your phi. Now you start the search for this E. You compare it to phi 120, and also you start running it through these GCD functions. So let's try this to motivate this a little bit more. I'm going to move to the next page just to make this a little bit cleaner. So here, let's imagine that you're in the algorithm, right? And you're going to iterate. And your first iteration, let's call it step 1, is going to be your candidate, if you will, is E E5. So let's do, well, actually, let's do it in order. So let's imagine that your candidates are 3, 5, and 7. Do you guys see that? So let's start with the first one. Your candidate is 3. So what you do is you ask, is the GCD between my current E and phi, let me use the letter here, and phi, is it equal to 1? So what is it here? In this case, GCD of 3, comma, 120. Do you guys see that? So what is the GCD of 3 and 120? Who can tell me? Yes, please.
Would it be 3?
It's 3, right? Very good. Exactly right. Do you see that? That's it. That's what the algorithm is doing. See how it seems hard, but at the end of the day, RSA is based on like very trivial math. So now, okay, does it meet the condition? No, doesn't meet the condition, right? Okay, so in the search, you continue. So now you try the next candidate for E, which is going to be 5. Okay, so the same thing. GCD 5, comma 120 equal what? So you go again. So what is the largest positive integer that divides each of two integers? Hmm? 5. Very good. 5. So once again, does it meet the condition of being equal to 1? No. So this would be a bad E for this encryption. So it's also rejected. Do you guys see that? And then you repeat the process again. So let's try another one. E equals 7. Okay. So GCD of 7 and 120. What is it? What is the result here? 1. So in this case, does it meet the condition? Yes, because it has to be 1. That's it. So that's the little step that I didn't introduce before, but I'm showing it to you now just so that you have an intuition of what's going on. And just remember, I'm not going to ask you to do this by hand, because the algorithm will do it, right? So and these are massive numbers anyway, so it wouldn't be practical. But yeah, so that's sort of the algorithm, okay? And it starts to get us closer to where we're going. So that's how you get E in this example. So in this example, we've got P and Q, we got N, we got phi. Now you have a better understanding of how to, through a search, try out to obtain E. And as it turns out, and that's why in the code, if you remember, on Thursday, we had that if statement, right? So we had to see if, is my E or something, is my N less than or greater than this? Okay. So if phi is larger than 65,537, then that's a number that we probably want to try because as we're doing the search for E, for that given N and that given phi, it just so happens that when we do this, 65,537, comma, phi, it will likely be equal to 1. Do you see that? So it'll work. All right. So that's why that's a very common E that is used. Okay. Any questions on that? All right, but that's where that's coming from. You can convince yourself as long as that number is less than phi and it meets this condition of being equal to 1, then that would be a good E. And it's commonly used. Okay. All right. So we did that part. We've done E. Now for completion, I'll do the D part. Okay. So if you guys remember, but this one we had already addressed. This one also, and you've already seen in the code on Thursday, it uses an algorithm, right? What was the algorithm to find D? So to find D, we use the EEA algorithm. All right, so this is another type of search algorithm, which is called the extended Euclidean algorithm. So I'm not going to go into the details of this algorithm, but if you're interested in understanding it, remember it's in the code that I provided on Thursday because all of that is written from scratch. So you can take a look. But I'll just give you fill in the details here. So this is the extended Euclidean algorithm. And that was in the code denoted by the function in, right? So it's some kind of an inverse function that works in our context. So imagine, if you remember, the condition is that D needs to what was it? D mod N, correct? Must equal 1. And we've already talked about this. This just has to do with the remainder, if you remember. So in this case, the Euclidean EA algorithm would do a search and then maybe discover that the algorithm is 103. Okay? So given that, we're going to plug in the values here. So 103 times, what was E? 7? Yeah, 7 mod N, which was 120, should be equal to 1, right? So we already discussed that. So how do we do this? Essentially, 103 times 7 should be 721. 721 mod 120, and this is going to be equal to 1. So then 721 divided by 120, that's going to be 6, which is 720, and the remainder is 1. You guys see that? And so it meets the condition also. Got it? All right, so this kind of just a review of everything, a final set of problems for this. Okay, and then after that, remember, as far as encrypting and decrypting, you just assume a message equal 9. Okay, so if we want to cipher, it's going to be M to the E. I'll use the percentage here. It's the same thing, mod N. So this one should be 9 to the 7 mod, what was it, 143? And it's 143. Yeah, this is, sorry, this I wrote incorrectly. This is feet. Just make a note of that. Yeah, guys, check your notes. All right. So let's do 143. So this should be 48. And then to decrypt it, C to the D mod N. So this should be equal to 48. D is what? 103 mod 143. Yeah. Okay. And this should give back our message, which is equal to 9. Any questions, guys? Make sense? All right, great. So this is that's the algorithm, all right? And we've covered also GCD. And so now we have this context. Okay. So now we're going to start focusing a little bit more on breaking RSA. Okay. So, but you already know how it works. So I'll just mention briefly what factorization is, and then we'll do the example with factor DB, so that you can actually try to break it. So how to crack RSA? RSA. So the goal is really to figure out what D is, and we kind of want to reverse engineer this. We know that we have the public key for sure. So that means we have E and N. We know that we want N so that we're able to factorize it and get P and Q. And from there, we need to calculate phi so that we can calculate D essentially. Okay, so that's basically the idea. So our challenge is to find, oh, sorry, this should be a P, Q and P. Yeah. So we know N, right? So that's the key here. So we have public key. So one of the assumptions is we know N. Okay. We know also that P and Q are prime numbers. And if the attacker has P and Q, he can figure out what P minus 1 is and Q minus 1 is, so he can solve for phi. Okay. So what we need is this thing called factors, right? So this is, again, another thing that you probably are familiar with. So what are factors? Factors. So these are the numbers you multiply together to get another number. That's essentially what it is. So, but because these are prime numbers, it's a little bit harder, right, to figure out. Okay, so factors are the numbers. Factors are the numbers you multiply together to get another number. Essentially, 2 times 3 equals 6. So obviously 2 and 3 are factors. That's it. Okay. So for instance, if we have another number, now we have a bigger number, let's say 12, I could ask you the question, what are the prime factors of 12? Right? So what are the prime factors of 12? So we know that we have 12, 6, for instance, times 2 is 12, but these are not the prime factors of 12. Prime factors of 12 would be 2 times 2 times 3, right? Yep. So that's it. So these are the 2 and 3 are prime factors of 12, essentially. That's the idea. So think about it. There's like a procedure. This is not how you would do it, but the idea is that to look at this so you can start thinking about how an algorithm would solve for this. Okay, imagine what you want is an algorithm, for instance, for the quantum computer, they use something called Shor's algorithm. Okay, and this actually, in theory, breaks RSA. So once a quantum computer is available, it's broken, I guess. Right? So that's what we're going to simulate. So we don't have a quantum computer, but we can simulate a quantum computer with Python by using a library. So that's one of the things that we're going to try out today, right? And learn a little bit about. So let's just do one last thing called a factor tree, just to kind of drive this point. So factor tree. Okay. So let's say now you want the prime factors of 48. So these are going to be the prime factors of 48. So you could do something like 48, and that's 8 times 6. And then you factor this one as 4 times 2. And as you can see, this is a type of a binary tree that is trying to figure this out, right? So in an algorithmic way, like you have seen binary trees in your data structures course. So 6 becomes 3 times 2. And you can see now we just have a few nodes in the tree that still need factorization, which is 4. So 2 times 2. You see that? And so this is kind of an algorithmic approach. So for 48, the prime factors would be 2 times 2 times 2 times 2 times 3. So they are essentially 2 and 3, correct? Do you guys see that? So hopefully you're seeing something very interesting here, right? So here we could have 3 and then 4 times 4 times 3. Do you see that? But then that 4 can be further broken or factorized into 2 times 2. So now you see why P and Q are actually what? Prime numbers. So what does that tell you? That they can't be broken up into further numbers, right? Because they are prime numbers. So that's an interesting observation of how this works, right? That it makes it harder to figure out the numbers. All right. So now we have this idea, okay? Obviously, when we have our n, it's just going to be these two numbers. They are prime numbers and they are massively large prime numbers, in fact. Okay? So that's the security. The process, you might imagine if it was just 48. Trivial, right? In a sense. I mean, you write this algorithm, you kind of figure it out. But so the algorithm is known for this. What makes it hard to solve for RSA is the fact that these are really large numbers and they're prime numbers, in fact. Got it? Any questions about that, guys? All right, great. So obviously, I'm not going to ask you to invent an algorithm or write an algorithm to do this. No one has been able to break this with like conventional algorithms. Okay, so instead, we're just going to use, two approaches. So at this point, no one has factorized really large ends, right, to find PMQ. So it's not known that this has been done. Maybe in like the top secret world, they've done it, but they're not going to tell you, right? So they would never tell you that. But in the public, in the literature, in the research, no one has successfully built an algorithm that can solve this. All right. Now, there are solutions, as I said, one being Shor's algorithm, but that's only for quantum computers. It's theoretical, as quantum computers don't exist yet. All right. But now we are ready then to start doing the quiz, right? So we're going to do the quiz, and then we're going to come back. There's a few additional little details that we want to learn about, like if we have a message that is longer than just like 56, how do we encrypt that? So that's a different idea. All right, so we're going to need the virtual machine for this part. So we're going to switch over to so this is a thing that you won't solve by hand. This is actually a computer-based example. And as I said, try to do this because it's similar to the scavenger hunt that's going to take place in 2 to 3 weeks. Okay, so and think of it as a fun task. All right, so I'm going to stop sharing this. I'm going to start up the virtual machine. And as far as submitting, all I need is a sheet of paper with your answer, because I need the numbers, right? So I'll need like, what is M, for instance? Okay. All right, so it should be a fun exercise. All right, so we are sharing the screen. So we're going to start the virtual machine. And we're going to go back to Thursday's script the RSA program, right? That's you. I won't change this going forward. So whenever I say break RSA, you should use that script. I mean, you should use that script. Okay, so let's start it. So there's two ways that we're going to solve this. First, I'm going to introduce something called factordb.com, and that's a website. That's a website, I guess researchers have been collecting P's and Q's, right, for years, right? And so there's a database that we can query sometimes, but those are for small on the smaller side, P and Q. So obviously they don't have something for like a seed of 1,024 or something like that. That would be bad if that existed. Okay. And then later, as time permits, today, we're going to add the quantum computer to try to do this again. All right. So should be starting. All right. So the quiz is very simple. I'm going to give you C, and I'm going to give you the things that would be public. Okay. And from there, you have to, solve the problem and find M. I'm going to use from the two problems that we did earlier today. I'm going to use one of those to show you how factor DB works. We'll do a couple of examples. Right, so if you remember the first problem we did, we had a P of 17 and a Q of 43, and then we had an N equal to 730. Right, so it's easy to go from P's and Q's to N, but now we need to go from N to P and Q. All right, there it is. So let's log in. And we're going to navigate to Thursday's script so we can have that available. So I believe we went over everything and it was working fine. So we can reuse that. All Final. So I'm gonna open the terminal. All right, here we are. So let's increase the size of this. All right, so let's go to that script. And let's navigate to fall 2025 TF 350. Okay, and our script is in RSA. All of our RSA scripts are in there. Okay, so you actually may need all of these. It's up to you how you use it. You can do the encryption and decryption just with the formulas. That's fine. But to figure out D, right? To figure out D, we need that inverse function, remember? And so that's only available in this script for the full code. I think we did the full code Thursday. So let's go there. You may need to do some changes, of course, but let's take a look. So RSA full code. Okay. Right. So if you remember, I'll remind you. Um, we have a function to generate prime numbers. We have this function, if you remember, in. This is a very important function, right? What does it return? Remember that if you give it E and phi, it gives you back D. That's the private exponent. That's the private key, essentially. And that's the thing that you want. So you need to use this function. Do you guys see that? You need to get D. But to use this function, what do you need to provide? You need to provide E and phi here. Do you see that? So you need to figure out those parameters. Okay, GenRSA. This is when we are creating our keys initially, but in this case, you're no longer following that pipeline. The pipeline you're following now is that you're trying to break RSA. So, you've stolen or you've borrowed the public key. So you already have E and N, right? So you don't need to recalculate N. Okay? You don't need to do that. Okay? So what you need to do is you need to figure out, so you may not need to use gen RSA, is what I'm saying. And then you have all these functions, which are utility functions for converting from text to lists, list to text, and so on. And then you have these functions for encrypting and decrypting. Now, the problem with these functions, and I want to stress this is really important. For today's example, you won't use these functions, the decrypt function. Why? Because I'm just going to give you a simple number that I want you to decrypt. But for the scavenger hunt, I will give you, some kind of a message that was generated with this encrypt function because it's going to be a string of some kind. Do you guys understand? So for the scavenger hunt, you will be using these functions. Okay. And I will give you a much more complex message that has to be formatted correctly. You guys remember how we encrypt something and it's like a list and then we pickle it, right? And we generate a pickle file. So that's what you can expect I will give you. I'll give you a type of a pickle file or something like that, um, or a list of values. And then you either have to copy paste that list into the code directly or read the pickle file. Make sense? Okay, make a note of that. All right. For that will be for the scavenger. But for this example, it's just going to be some integers. All right. So and then here is the process. So what do you need to do? Do you need to generate P and Q? No. Don't need to generate P and Q. So instead of invoking get prime here, comment it out and plug in your values here. Okay. This is the same thing that you will have to do on the scavenger. So once you factorize n into P and Q, you just plug the values in here. Okay? All right. And then once you have those values, um, this you can run it if you like, but remember that you have E and N, and what you're trying to figure out is D because you also already have N. So really the function that you will need is, where is it? It's in Gen RSA, right? Gen RSA gives you back the D exponent that you need. So what you need to provide here are whatever these parameters are. So you go to Gen RSA and you look in here, and Gen RSA wants P and Q. Okay? Calculates N, calculates phi, and then it provides given N is going to select one of these two, and it's going to return, given the phi, is going to return the D exponent that you need. Got it? Any questions, guys, about this process? So this is what you're going to try out today to see if you can do it. Okay? And then once you have D, just use the equation approach. What I mean by that is use the TOI script. It'll make it easier so that you're not so concerned with the formatting. So just go to TOI RSA. TOI RSA. And so the same thing, you're going to use which one of these? Decrypt, right? So you're going to have, I'm going to give you C, that's the mystery. And you're going to have this D value and N, and you should get the value. Got it? That's it. And then this is your answer in your quiz. And also give me D. I'd like to know what D wants. Okay? All right, great. So that's the scripts that you have to use, right? So one script for finding D, and the other script for just doing the decryption manually. So essentially, you're just doing the equation M equals C to the D mod N. That's it. All right, so here is now how you're going to factorize. So there's, as I said, two ways. In this exercise, we're just going to use factordb.com, but in another exercise, we'll use the quantum computer. Oops. All right, so what do we need for this? We just go to the website. So we open up the browser. And let's just try some numbers. Let's try to factorize a few things, right? And see if it works. Okay, so here just type factordb.com, factordb.com. Okay, perfect. So that's it. So this is the website. So essentially here, you just factorize. As you can see, there's a lot of features, but you just have to use this text box and press this button. And this is, our first example, a simulation of a quantum computer. So let's try 731. 1743. Do you guys see that? If you look closely, this is the first problem we did today. So I had a P of 17 and a Q of 43, and I was able to calculate my n from that. So now I'm reversing the process from 731 to 17 and 48. But remember, these are prime numbers, so there's only two of them in the factorization. Got it? That's it. All right, so let's just do a couple more, and then you can start trying to solve the challenge. So we did. Hmm. That one, and then we did. Yeah, we did this one. So by 143 factorized 1113. So that was problem number two that we did today. I had a P of 11, Q of 13, and multiplied them. That gave me 143. Now I'm reversing the process and I get my P and Q. Got it? That's it. So, all right. So now let's pull the problems we did, unless we did another one. Yeah. Okay, so now we can start the quiz or challenge. All I need, like I said, is a sheet of paper. Write down your D and your M. Okay, so let me switch back to the whiteboard, and I'm going to give you the parameters. And it should be, and ask questions. Feel free to ask questions. And the whole point is to practice this so you can do it on the scavenger. Switch to the whiteboard. Okay, so this is going to be our quiz. Break RSA. All right, so what would you have? So the secret message is this. This is the cipher, C. And let me get this right because it's 32664056. That's your cipher. So 32664056. So you intercepted this message. And you know, obviously, Bob sent it to Alice, so you know who the two parties are, and you were able to intercept the correct public key, which will be 65 537, comma 221 08 3007. So 221 08 3007. All right, that's it. Break it. I can pause this recording somehow.